So let's get started. Not too many people in the room yet, but hopefully you're watching this on YouTube. At least the people in the room should get something out of this. General ideas today, we're going to do practice problems for conservation of momentum. Well, conservation of momentum really doesn't have too many equations. It's mostly that initial momentum equals final momentum in any collision. Well, momentum is mass times velocity. Of note, really, there should be arrows above this too, because we have to worry about the fact that everything is a vector. I just forgot to put them there. So I like to sometimes talk about when I do old exam problems. The first question, the second problem, and the third question are old exam problems, the kind of thing you might see on an upcoming exam. The fourth one, which I hope to do today, is a little more complicated, and it's like stuff on the homework, but it's a little more complicated than something I'd put on an exam. And to jump right in, this first problem says, Spider-Man jumps towards Dr. Octopus at 18.3 meters per second in an attempt to capture him. So we have Spider-Man is traveling at 18.3 meters per second. So I'm saying Spider-Man initial. In an attempt to capture, seeing Spider-Man approaching, Dr. Octopus throws a car at Spider-Man at 9 meters per second. Spider-Man sticks to the car in the air in a completely inelastic collision. What is the velocity, magnitude, and direction of Spider-Man and the car after the collision? Giving the mass of Spider-Man as what, 76? Dear God, I have Spider-Man's mass memorized because I've done so many problems with it. And the mass of the car is 1240 kilograms. Now, first thing I'm going to say, I already wrote down something wrong. Something is inherently not correct on this page, which seems weird because I matched exactly what it was written there. Spider-Man moves at 18.3, the car moves at 9, and here's the masses. But here's the thing. When dealing with momentum, it is a vector. And I know I'm going to be dealing with momentum because this is a collision. It even says a completely inelastic collision. The word collision was used, making it very obvious it's a collision. When you're dealing with that, you have to deal with the vector notion of things. That what direction something in is important. And when I look at that call, the arrow on it is to the left. Because that arrow is to the left, that means it's moving to the left. And if I use a standard coordinate system, right, like the normal x is to the right, y is up, to the left is in the negative direction. So I have to remember to say that this call, its velocity is not 9 meters per second. The magnitude of its velocity is 9 meters per second, but its velocity is negative 9 meters per second because it's to the left. This is the place where it's most common to make a mistake on these problems. But once I have that, what I'll say is initial momentum equals final momentum, where momentum equals mv. And I'll just look at the system. And I'll look at that picture and say, okay, initially I have Spider-Man moving because there's a Spider-Man there. So in my initial, I have the mass of Spider-Man, the velocity of Spider-Man initial. My initial picture also has a moving car. So I'll say I have the mass of the car, the velocity of the car initial. And then Spider-Man sticks to this car. That means they're going to move as one unit. So I'll just treat them as one thing. One thing that has a mass of Spider-Man plus car, that was supposed to be an S, but I failed, and is moving at some final velocity. There is my equation. I'm just saying, let me highlight what I want to highlight. I'm just saying the momentum of this plus the momentum of this equals the momentum there. Past that, it's all math. I want to find the final velocity, magnitude, and end direction of the car. So I'm going to take this equation and divide both sides by the bit in parentheses. And so it would be the mass of Spider-Man, velocity of Spider-Man initial, plus the mass of the car, velocity of the car initial, over this total mass. Now, when I do that math, I get negative 7.42 meters per second, which is an acceptable answer. But I did say magnitude and direction. And so what I'll do is I'll look at this and say the magnitude is 7.42 meters per second. And the direction is to the left. I know it's to the left because I got a negative answer. And a negative answer just means to the left. He's going that way. Which I mean kind of makes sense. If someone throws a car at you, you're probably going to go with the car. You're not going to really overtake a car and go fast, go with it, right? Let's be logical here. And that's kind of it. That's the general idea. For all of these problems, we'll say initial momentum equals final momentum, where momentum equals mv. And we'll just look at our picture, write down my initial, write down my final, and solve. Questions? I'm going to go to the next problem. Now that problem was completely inelastic. This problem is going to be something that is not completely inelastic, and people bounce off each other. Fun fact, so this one is a reference to Thor Ragnarok. The scene in here was actually in the trailers, and I actually did this problem on the exam before the movie came out. And by luck, the exam this was on was the exact same day the movie came out. And so after taking the exam, I then went to see the movie. And by luck, a whole bunch of my students went to see the same showing. And after the movie, said they were really fucking pissed at me because during this scene, all they could think about was the physics exam they just had. Because that's the type of asshole I am. Anyways, what I say here is in Thor Ragnarok, Thor and Hulk leap at each other in an arena. Before the collision, Thor is traveling at 11.2 meters per second. So velocity of Thor initial is 11.2 meters per second. And meanwhile, Hulk is traveling at 10.8 meters per second. But I'm looking at my picture. My picture shows Hulk going to the left. If he's going to the left, his velocity is in 10.8. It's negative 10.8. They say after the collide, Hulk flies backwards at a rate of 9.72 meters per second. So that's my Hulk final. Now here it is positive because that's to the right again. I'm just looking right at my picture. And I said, given the masses, the mass of Thor is, mass of Thor is impressively heavy. 290, really, cat? Come on. And the velocity of Hulk is 635 kilograms. What is the velocity of Thor final? Just off camera, you can't see what my cat is getting ready to jump again. Now, if I want to solve this, I have to follow the same logic. I'll say initial momentum equals final momentum, where momentum equals mv. But this time I have the same, basically exactly the same thing for the initial. The initial hasn't really changed at all. But in the final, they're not stuck together. I have Thor moving, I have Hulk moving. And so what I'll do is I'll just treat them separate. I'll say my initial is the mass of Thor, velocity of Thor initial, plus the mass of Hulk, velocity of Hulk initial. And my final will be both of them also. The mass of Thor, velocity of Thor final, plus the mass of Hulk, velocity of Hulk final. Any questions there? Because that's the crux of it. Now I want this number, the velocity of Thor. And since this has that piece added on, I'm going to subtract this. I'm going to take this bit, and I'm going to subtract it from both sides. And say the mass of Thor, velocity of Thor initial, plus the mass of Hulk, the velocity of Hulk initial, minus the mass of Hulk, velocity of Hulk final, equals the mass of Thor, velocity of Thor final. What I can then do is divide both sides by Thor's mass. and plug in some numbers. And what you get is negative 33.7. Or you get 33.7 meters per second to the left. Which, I mean, it's the Hulk. Of course he wins. Hulk is the strongest there is. That's the general idea. Initial momentum equals final momentum. Well, momentum is mv. That's how you solve all of these. Like, I'd like to say, here's the secret to doing them, but there is no secret to doing them. It's just you plug into this. I guess that is the secret. They're pretty straightforward. Questions? Now, both of these problems were left and right. One was this, the other one was that, but both of them were all left-right. You know, just colliding or bouncing. This also works in the up-down sense. This problem is about Street Fighter, because I love my classic video games. And what it says is Ken from the Street Fighter series is known for his Shoryuken, which is a jumping uppercut. Ken's opponent, M. Bison, jumps towards him and is falling at a rate of 1.17 meters per second. That means the velocity, I'm just going to put B for Bison. He is falling at 1.17 meters per second, but he's falling. That means he's going downward. It means he's moving in the negative direction. And while we're doing that, Ken begins to rise upwards at 3.21 meters per second. So the velocity of Ken initial is 3.21 meters per second. Ken then connects with the Shoryuken, after which he's still traveling upwards. But now he's traveling at 1.45 meters per second. What's the velocity of Bison final, given their masses? Well, the mass of Bison is 80 kilograms, and the mass of Ken is 75 kilograms. So the general idea is someone's falling, someone else is coming up with a fist, he punches and keeps going up. Logically, Bison should be going up, because if he's falling, coming up, and then afterwards is going up, just would make sense. The Bison should be going up also. Should be guy like punching through him, basically. Now, because it's up and down, I still have to work my negatives, but here the negative, the idea is just right there. My arrow is going down. My original green arrow on Bison. Bison was falling, so I have to say he has a negative velocity. And so, yeah, I'll just put that velocity as negative, because he's moving downwards. And I'll say equations. Well, I know the equation. It's momentum. There's only one equation. Two equations. P equals mv. Sorry. P initial equals P final, and P equals mv. And I'll say, looking at that picture, initially, we have Ken moving. The mass of Ken, velocity of Ken initial. Also in my initial, I have M Bison moving. The mass of Bison, velocity of Bison initial. After the flaming punch, we have Ken moving, mass of Ken, velocity of Ken final. And Bison moving, mass of Bison, velocity of Bison final. Now I want to solve for the velocity of Bison. And so what I'm going to do is I'm going to subtract this blue term from both sides. And say the mass of Ken, velocity of Ken initial, plus the mass of Bison, velocity of Bison initial, minus the mass, I'm solving for Bison. Mass of Ken, velocity of Ken final, equals the mass of Bison, velocity of Bison final. And then I'll divide both sides by this mass. The velocity of Bison final equals the whole top again. Which I'll use to plug in my numbers. Oops. And I get positive 0.48 meters per second, which means his velocity, the velocity of Bison final, is 0.48 meters per second and is upwards. It's upwards because it's, oh, I'm off the bottom. It's upwards because it's positive. If it was downwards, it would have been negative. And yeah, he goes upwards by doing like that noise that Street Fighter is wont to do. As I said, these are all old exam problems so far. No, well, didn't mean to do that. Questions? Is this making sense? Is there anything I can show? Okay. If you guys are all good, I'll make this shit complicated. And I'm going to do a problem. Now, we've actually done a second problem, but the exact same scene once before. But, you know, whatever. Sometimes there's only so many scenes I think of sometimes. A lot of Marvel today. That happens. That happens. My wall of Marvel comics behind me. Not even all the comics in the room. And this says, in the first Avengers movie, there's a scene where Black Widow is boosted directly upwards, and she grabs onto a speeding Choi Speedo and hangs on. Let's say Black Widow, who has a mass of 59.4 kilograms, so mass Widow is. What was that? Or was that not to me? Okay, I assume that's not to me. And since he's traveling upwards at 3.25, well, let's look at this problem. All the problems we did so far were nice straight lines. We had coming across sticking together, we had coming across and bouncing, and we had coming up and going up. But this one we got like she's going up and it's going that way, and like we got vectors and shit. This is two-dimensional. When I look at this, I say, now I can't just say this is positive direction, this is negative direction. That one vector is at a 20-degree angle. I'm now going to need to think about how to do this two-dimensionally. See, I say Black Widow is traveling directly upwards at 3.25. That means the velocity of Widow initial, which I gave the value of 3.25 meters per second. But if I'm working two-dimensionally, as I'm now doing, that I have not vectors straight together or apart, but at angles, I got to think about what direction they're in. And I can say Widow is traveling straight up. Now, if I compare this to a standard coordinate system, you know, X, Y, what I'll say is if she's traveling straight up, she's traveling in the Y direction. So I'd say that velocity of Widow initial is in Y. And she's traveling straight up. She's not moving side to side at all. So the velocity of Widow initial in X, or Vwix, will be 0 because she's traveling straight up. The Speedle, before she grabs on, has a mass 204 kilograms. Da, da, da. And it's moving at 25.8 meters per second at an angle of 20 degrees below the horizontal. That means it's going at 2.45 that way. But it's at some weird angle. I know anytime my velocity is at an angle, I need to break the components. I'm going to want to break this into its x component and its y component. Or to draw this in a more traditional sense, this arrow would be over here. And what I'll do is say, let's split that up. See, I'll say the velocity of speedo initial in x, and the velocity of the speedo initial in y. I can find those components. The components of x will just be the velocity of the speedo initial cosine of its angle. And its y will be the velocity of speedo initial sine of its angle, which will be the 25.8 meters per second cosine of, and I could do this a few different ways, but I'm just going to define this as negative 20 degrees. The reason why is because it's in the opposite direction as normal. We normally define positive as going counterclockwise, and this went clockwise. So I'm just going to make it negative. And this guy here will be 25.8 meters per second sine of negative 20 degrees. And I'll do both pieces of that math. 24.24 and negative 8.82. Questions? We still good? See, I'm still going to say P equals MV and P initial equals P final. But this P initial equals P final, really, I'm going to break this into two different equations. I'm going to say P initial in X equals P final in X. And I'm going to say P initial in Y equals P final in Y. And I didn't actually read the rest of the problem. I just went through it. They said, she holds on, we have a completely inelastic collision. What's the velocity afterwards? So what I'm going to say is after the collision, what's going to happen is that the Black Widow and ship combination will be moving at some angle. Possibly down, possibly up. We're not quite sure which. It's probably going to be down. But what I'm going to do is say its final velocity will have a x and a y component. I don't know what that x and y component are. I'm just going to call it Vx and Vy, but I'll solve for those terms. And when I know those terms, I can get magnitude and direction. Sorry. Okay. So I'll look at this and say, okay, in X initially, the Black Widow's not doing anything. She's jumping straight up. She's not moving in X. So in X, when I look at this, what I would say is that the only thing moving in X is the speedo. So I have the mass of the speedo, the velocity of the speedo initial in X, and that's my entire initial. Afterwards, the Black Widow and the speedo are together and be treated as one object with some final velocity in X. And I just wrote Vx, Vy though. I really should have put it as V final X, V final Y. That got messy. Yeah. V final Y. If I divide both sides by the bit in parentheses, I get that V final X equals MSV6 MW plus MS, which is going to be the mass of the speedo, 204 kilograms, times 24.24 over 59.4 plus 204 18.78. That's the x component. Meanwhile, I can look at y. See, in y, I can say my initial case, she's going up, it's going down. And so in y, my initial will be the mass of widow, velocity of widow, initial in y. And the mass of the speedo, velocity of the speedo, initial in y. And at the end, they'll combined as one item. And just like last time, I'll divide by this bit in parentheses. And plug in. So 59.4 times 3.25 plus 204 times negative 8.82. Am I off the side? Nope. 59.4. It's a 9 plus 204. And there we go. I now have the y component. And I can say, and I want to get rid of some of the stuff above for a second. I can say, hey, I know the x component and I know the y component. If I want to get magnitude and direction, well, magnitude, and I'm just going to kind of box this here, v final is going to be the square root of v final x squared plus v final y squared, or the square root of 18.78 squared plus negative 6.101 squared. Direction will be the inverse tangent of y over x. This is how I can make it complicated. The only way to make these complicated, really, other than having multiple collisions in the same problem, which is just a dick move. I'm not beyond doing a dick move. There used to be one of the homework like it, but I took it off a few years back. Is to go two-dimensional. But if you do two-dimensional, it's not really any harder. It's just you do the problem twice. One in x, once in y. So, questions. So anything I can do to help with these problems? Okay. If you guys don't have anything, that's all I got for you. Next week, we are going to basically redo everything we've done so far in the class. Spinning. That's the next two chapters. It's revisiting kinematics, revisiting forces, revisiting energy, revisiting momentum, but for the case when something is spinning. So you have that to look forward to. Other than that, have a good day. I'll see you Monday. Hope you have a great weekend. Bye.